This is the first of several videotapes on geometry. In these tapes, we will introduce the basic figures and concepts of geometry. We will start by discussing lines and angles, move on to triangles and quadrilaterals and circles, and learn how to find the perimeter and the areas of these figures. In all of our work, we will be assuming that we are working in plane geometry, that is, geometry of a flat surface like the blackboard. Okay, all of our figures will be drawn on this flat surface. Okay, so let's get started. Now we're not going to be able to define every term, every word. Certain concepts we will take as undefined, but everyone will understand what we mean. For example, as undefined, we will take a point and a line. Okay, we'll all know what we mean by a point and a line. And we'll start from here. Now, while a line continues indefinitely in both directions, a half line or a ray has a fixed point, an end point, and then continues in one direction only. Okay, a line continues indefinitely in both directions. Sometimes you'll see arrows, okay, on the line to indicate that it's just continuing. A half line or a ray has a fixed end point and then continues in one direction only. If you take two half lines with a common end point, we form what we call an angle. You can think of an angle of any size as being generated by a half line or ray, which rotates about a fixed point, which we will call the vertex, from an initial side to a terminal side. Okay, and an angle, like I said, an angle is generated by a rotation. A complete rotation is considered to be one of 360 degrees. In that case, the terminal side will swing all the way around and come back to the initial side. Complete rotation is one of 360 degrees. This is a complete rotation. Okay, we measure angles in degrees. I will say an angle of 30 degrees, where I mean the measure of the angle is 30 degrees, just like you'll say, oh, the person is 200 pounds, okay, where you mean that he weighs 200 pounds. So you'll understand when I say a 30-degree angle, the measure of the angle is 30 degrees. Okay, now, there are certain angles that are particularly important. We have a 90-degree angle. A 90-degree angle is one which is generated by 90 360ths, or 1/4 of a complete rotation. Okay, so in such a situation, your initial side will look like that, and your terminal side like that. Here's your initial side. Here's your terminal side. Okay, it's an angle of 90 degrees, 1/4 of a complete rotation. Such an angle is called a right angle. And we usually put a little symbol in there, a little squared off symbol here to indicate that these lines are perpendicular to each other. Perpendicular lines meet at right angles. Okay, an angle of 180 degrees is generated by 180 360ths of a complete rotation. That is, by 1/2 of a complete rotation. Okay, in such a case, your initial side looks like this, and your terminal side, here is 1/4 of a complete rotation, is going to be over here, 1/2 of a complete rotation. Here we have an angle of 180 degrees. Such an angle is called a straight angle, since the initial side and the terminal side, these two half rays, come together and they form just a straight line. This is called a straight angle. Angles between 0 and 90 degrees are known as acute angles. If they're between 0 and 90 degrees, not including 0 or 90, okay, we call them acute angles. And from 90 to 180, between a right angle and a straight angle, we call these angles obtuse. Now, an angle can be designated in various ways. If there is no question about what angle we mean, for example, something like this, okay, this angle in here, we could just give it one letter and we'll say that this is the angle A. This symbol can be used for angle. If, however, we have a situation where we have adjacent angles, okay, those are angles that have a common vertex and a common side between them, something like this, then just saying angle A would not be sufficient. Okay? In such a case, we would designate our angles by usually 3 letters with the vertex in the middle. For example, when I say angle A, it's not clear. Do I mean angle BAD, the entire angle, or do I mean BAC, the lower angle here, or CAD? So when you have this ambiguity, we usually use 3 letters to denote the angle. Okay, for example, this angle over here is angle BAC. As I mentioned before, these angles here, BAC and CAD, are adjacent angles. Angles BAC and angle CAD are adjacent angles. BAC and CAD, they share a common vertex and a common side between them. Angles which add up to 90 degrees are known as complementary angles. Okay? 2 angles which sum to 90 degrees are called complementary angles. For example, an angle of 30 degrees and an angle of 60 degrees. 30 degrees and 60 degrees are complementary angles. Complementary angles. Angles which sum to 180 degrees are called supplementary angles. Okay, if they sum to 180 degrees, they are known as supplementary angles. For example, what is the supplement of 60 degrees? Okay, the answer would be 120 degrees, since 120 degrees and 60 degrees gives you 180 degrees. Answer, 120 degrees. Okay, now I want to distinguish between an axiom and a theorem. An axiom is something that we will accept without proof. It's something that's intuitively plausible. It's a first part of the geometry. We have certain axioms, things that we accept. Okay, now as an example of an axiom in geometry, we have 2 points determine a straight line. This is an example of an axiom. 2 points determine a straight line. Okay. This makes sense. You've seen this before, that if you have 2 points, there is one and only one line that you can, two points which are not coincident, there's one and only one line that you can draw through these 2 points. And we accept this without proof. Okay, as an example of a theorem, something that we have to prove, we have something like this. Theorem, vertical angles are equal. Now, what do I mean by vertical angles? Vertical angles are the opposite angles formed when 2 straight lines intersect. Okay, let's call this angle in here A, B, C, D. Okay, I'm not using the standard notation. I could have labeled them in the traditional 3-letter way. I just want to bring out a point here. Okay, vertical angles are equal means that the opposite angles formed when 2 straight lines intersect are equal. Angle A equals angle C. A equals C. These are the opposite angles. And angle B equals angle D. Now, this is a theorem, something that we can prove. In fact, in a moment, I will prove it for you. Okay, now let's see how we can use it. If you know one of these angles, you can find all of the others. Let's say, for example, that we know that angle A is 30 degrees. If angle A is 30 degrees, then angle C must be 30 degrees. Since angle A and angle B together form a straight angle, okay, we have here a straight line. Angle A and angle B form a straight angle, therefore they add to 180 degrees. Angle A and angle B must be supplements. They're supplementary angles. If one is 30, then the other one, B, must be 150. And similarly here, well, if B and D are vertical angles, and if B is 150, then D is also 150 degrees. Of course, we could have reasoned our way around this way, saying, well, this is 30, and they form a straight angle. This must be 150. But now, B and C form a straight angle. You get 100, so this must be 30, because 150 and 30 gives you 180. And if that's 30, then since these two form a straight angle, 30 and 150 would give you the 180. And in fact, the proof works along those lines, making use of the fact that you have various straight angles in here. Let me give you the proof of vertical angles are equal, just to show you the difference between something which we accept without proof and something which we are capable of proving. And here is what we're trying to prove. Theorem, vertical angles are equal. And let's set up the diagram that we had before. Angles A, B, C, and D. Okay, now, the proof goes along these lines. Angle A and angle B together form a straight angle. Okay, therefore angle A and B add to 180 degrees. Okay, angle A plus angle B will 180 degrees. Okay, now angles B and C also form a straight angle. Therefore, and here is what we're trying to prove. Theorem, vertical angles are equal. And let's set up the diagram that we had before. Angles A, B, C, and D. Okay, now, the proof goes along these lines. Angle A and angle B together form a straight angle. Okay, therefore angle A and B add to 180 degrees. Okay, angle A plus angle B will 180 degrees. Okay, now angles B and C also form a straight angle. Plus angle B equal 180 degrees. subtracting the second equation from the first, which is something that we can do. Two things are equal. We can always subtract, right? Angle C plus angle B equals 180 degrees. These two things are equal. We can subtract the same quantity from both sides of an equation. Okay? Or if you prefer, you can multiply by -1 and add. Okay? Subtracting angle A minus angle C, okay, plus angle B minus angle B, which is just 0, equals 180 degrees minus 180 degrees, which is 0. And this gives us, adding angle C to both sides, let's put these symbols in so you can see it. Adding angle C to both sides, we get angle A equals angle C. And we subtracted angle A minus angle C. Here, angle B minus angle B gave you 0. 180 degrees minus 180 degrees gave you 0. And adding angle C to both sides, you get angle A equals angle C. These vertical angles are equal. And in a similar fashion, we can show B and D are equal. All you would have to do is to start with the straight angles involving B and D. In other words, say B plus C equals 180 degrees, and D plus C equals 180 degrees. And we would get the relationship that angle B equals angle D. So this is an example of a proof of a theorem. Okay, now sometimes problems in geometry give rise to first-degree equations, which we studied, of course, in algebra. Let me give you an example. An angle is 30 degrees more than twice its complement. Find the angle. Okay, it's a word problem in geometry which is going to give rise to a first-degree equation. Okay, now when I say an angle is 30 degrees, I mean the measure of the angle is 30 degrees. We can let x equal the number of degrees in the angle. And then 90 minus x would be the number of degrees in the complement of the angle. Since complementary angles add to 90 degrees, if x is the number of degrees in the angle, then 90 minus x is the number of degrees in the complement of the angle. Together, of course, x and 90 minus x add to 90, the number of degrees, okay, in a right angle. Okay, now let's try to express this statement, okay, algebraically. An angle, and x is representing the number of degrees in the angle. The angle is 30 degrees more than twice its complement. Well, twice the complement, 2 times 90 minus x, and then plus 30. Okay, the number of degrees in the angle is 30 more than twice the complement. The angle, or the number of degrees in the angle, is 30 more than twice the complement, 2 times the complement. And using this, we can solve for x. We get x is equal to 180 minus 2x plus 30, distributing the 2 through the parentheses. 2 times 90, 180. 2 times minus x minus 2x. Now, x is equal to 180 and 30. That's 210 minus 2x. Just added the 180 and the 30. Adding now 2x to both sides. 3x equals 210. Dividing both sides by 3. X is equal to 210 over 3. X is 70. Okay, so the angle that we're looking for is 70 degrees. Answer, 70 degrees. This angle, 70 degrees, is 30 degrees more than twice its complement. Its complement is 20. 70 and 20 give you 90. Its complement is 20. Twice its complement is 40. It is 30 more than twice its complement. 70 is 30 more than 2 times 20, or 30 plus 40. Now, the next thing I want to discuss with you is the idea of parallel lines. Most of you have heard the term before. It's sort of hard to come up with a workable definition for parallel lines. You might think of these as lines in the same plane. Of course, we're always working in the same plane. For example, in the blackboard, we don't have a line coming out of the blackboard. This is plane geometry. Okay, lines which never cross no matter how far they're extended. Okay, lines which never cross no matter how far they are extended. Or another possibility would be lines which are always the same distance apart. Lines which are always the same distance apart. The trouble with these definitions is that it's very hard to check to see if these lines will never cross no matter how far they're extended. How are you going to go around checking? You can't extend them forever. And also trying to check that they're always the same distance apart. I mean, always. It's something that it really can't be checked out. But I think we all know what we mean. Okay, lines which look nothing like that. No, but that's the idea. Or the idea being that they would always be the same distance apart, and they would not cross no matter how far they're extended. Okay, if you want, even if they don't look parallel when I draw them, if I want to indicate that they're parallel, I can put, say, little arrows in here, meaning that the lines are going in the same direction. Okay, these symbols, okay, the 2 arrows like that going in the same direction will indicate that these 2 lines are meant to be parallel. Now, parallel lines have certain interesting properties, and when we study these properties, we will come up with better ways to define them. If we take 2 parallel lines, 2 or more, doesn't matter, 2 parallel lines, and we draw a line which crosses these lines. Such a line is called a transversal. Transversal. It's a line crossing 2 or more other lines. You have parallel lines here, and they're being cut by a transversal. If parallel lines are cut by a transversal, certain of the angles that are formed, you see these lines with the transversal form certain angles. Certain pairs of these angles are equal. Okay. If parallel lines are cut by a transversal, one, the corresponding angles formed are equal, and I'll define what I mean by these terms in a second. This corresponding angles are equal. And 2, the alternate interior angles are equal. Okay, let me number the angles in the diagrams. We have, let's say this is an angle 1. That refers to this angle here. Angle 2, angle 3, angle 4, angle 5, 6, 7, and 8. In each case, it's clear what I mean. Angle 1 runs from here to here, and so on. Okay, now let me explain which are the corresponding angles, which are the alternate interior angles. Corresponding angles are the angles which sort of have the same position with respect to the parallel lines in the transversal. For example, 1 and 5 are considered to be corresponding angles. Angles 1 and 5 are both above a parallel line and to the right of the transversal. They're occupying like the upper right-hand corner here. They're not really corners, but you get the idea. They are, in both cases, angle 1 and angle 5, they are to the right of the transversal and above the parallel line. Angle 1 and angle 5 are corresponding angles, and they are equal. Okay, so examples of corresponding angles. Angle 1 equals angle 5. Okay, similarly, we have angle 2 and angle 6 as corresponding angles. Angle 2 and angle 6 are both above the parallel lines and to the left of the transversal. So angle 2 equals angle 6. Similarly, angle 3 and angle 7 are considered corresponding. They are both below the parallel lines and to the left of the transversal. Angle 3 equals angle 7. And we have another pair of corresponding angles, angles 4 and 8. In both cases, they are to the right of the transversal and underneath their respective parallel lines. Angle 4 equals angle 8. Okay, now, alternate interior angles. Alternate interior angles. Alternate interior angles. Interior because we're talking about angles inside the two parallel lines. Alternate because they are on opposite sides of the transversal. Angle 3 equals angle 5. 3 and 5 are considered alternate interior angles. Interior, they're on the inside. In other words, we have 4 interior angles here, 3, 4, 5, and 6. The alternate ones are 3 and 5, which are on opposite sides of the transversal, and 4 and 6. Angle 3 equals angle 5. Angle 4 equals angle 6. So we have here corresponding angles. You might think of corresponding angles as forming some part of, they help to form some part of the letter F. In other words, you have a situation, parallel lines being cut by a transversal. For example, these angles. If you think of this as an F, these angles are equal, or if you consider the upside down F here, these angles are equal, and so on. They generate different pairs. Okay, the corresponding angles. Parallel lines cut by a transversal, the angles which occupy the same position with respect to the parallel lines in the transversal. And they tend to form some kind of an F. And similarly, the alternate interior angles tend to form some kind of a letter Z, although it may be, a mirror image of it. If you have parallel lines cut by a transversal, these are alternate interior, and you see the letter Z in here. Or it could be a Z backwards here, like a mirror image. These angles are also equal. The alternate interior angles, like forming part of a Z, the corresponding angles forming part of an F. Now, if you know, oh, by the way, these corresponding angles being equal could be taken as a better definition of parallel lines. So if you have lines being by a transversal and the corresponding angles are equal, that would mean that the lines are parallel. They would have to, therefore, stay the same distance apart, and they would never cross no matter how far they were extended. So these angles give us better definitions of the term parallel lines. Now, if you know one angle, say, in a setup here with the parallel lines and the transversal, it's usually possible to get all of the other angles. For example, so we have parallel lines cut by a transversal, and I'm telling you that this angle is 50 degrees, and I ask you to find all of the other angles. Okay. There's a variety of ways of doing it. You could, for example, make use of the fact that 50 degree, that these are vertical angles, without even using anything to do with the parallel lines. Straight lines intersect the opposite angles, of course, here must be equal. Now, since 50 and whatever angle is in here together form a straight angle, it is clear that this angle must be 130 degrees. 50 and 130 forming a straight angle. And if that's 130, this is 130, once again by vertical angles, or you can go around with the argument of straight angles. 50 and 130 form 180, 130 and 50 form 180, and so on. Now, since these lines are parallel, we have the corresponding angles equal to what they have over here. For example, this angle must be 50 degrees since it is also to the right and above the transversal. To the right of the transversal and above the parallel line. This angle here is 130 degrees to the left of the transversal and above the parallel line. This must be 50. It corresponds to this. This must be 130. Okay, so knowing one, it is possible to figure out many of the other angles. And this brings us to the end of this tape.